The Webb is tremendous to such an extent that light has been traveling for more than 13 billion years. The universe has been growing, and thus, the light has been stretching from the most distant universes. We're essentially looking back in time, practically to the Big Bang. The boundlessness of the universe might seem colossal, yet every single piece of it began from what we refer to as the singularity. This is how we interpret the theory of how things came to be. The James Webb Space Telescope, JWST, has uncovered colossal mysteries about the birth and evolution of the universe, leaving us astounded. Renowned physicist Brian Cox has announced that the groundbreaking discoveries made by the JWST could reshape our understanding of the universe as a whole. Join us as we delve into these monumental revelations that promise to revolutionize our perception. The James Webb Space Telescope, named after the eminent NASA Administrator James E. Webb, stands as a marvel of modern space exploration. This telescope represents a significant technological leap forward from its predecessor, the Hubble Space Telescope. A collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses its predecessor's capabilities. Using cutting-edge technology and a design optimized for studying the universe in detail, the JWST provides clear and sharp images of distant celestial bodies, primarily operating in the infrared range. This unique feature allows it to penetrate vast dust clouds and capture celestial objects previously hidden from view. With its large 6.5-meter primary mirror, composed of 18 hexagonal segments, the JWST dwarfs Hubble's mirror in size. Positioned about 1.5 million kilometers from Earth at the second Lagrange point, L2, it orbits the Sun alongside Earth, ensuring a stable and uninterrupted view of the universe. Studying the farthest corners of space, light years away, involves a form of time travel. The JWST uses infrared instruments to observe celestial objects and events from billions of years ago. The light emitted by these objects, due to the expanding universe, undergoes a redshift, moving from the visible spectrum to the infrared range or longer wavelengths. Thankfully, the JWST can detect this infrared light emitted by these distant bodies, enabling scientists to study the birth of stars, explore galaxy formation, and analyze exoplanet atmospheres. Its most recent groundbreaking discovery includes identifying a vast collection of galaxies at the edge of the observable universe. This challenges the validity of the theory of the universe's origin, prompting a reassessment of our fundamental cosmological assumptions. To better understand how we arrived here, let us take a brief journey through the history of space exploration. Early advancements, such as those of the Greeks and Chinese, laid the foundation for understanding planetary motion by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the 20th century, Edwin Hubble, a renowned astronomer, made significant contributions to cosmology and observational astronomy. His observations revealed that distant nebulae were separate galaxies far beyond the Milky Way, altering our understanding of the universe's size and expansion. Hubble's law demonstrated that galaxies farther away were receding at faster rates, providing evidence for the expansion of the universe. The post-World War II era marked the beginning of the space race, with milestones like the Soviet Union's Sputnik in 1957, Yuri Gagarin's orbital journey in 1961, and the Apollo 11 moon landing in 1969. Fast forward to 1990, when the Hubble Space Telescope was launched, offering unprecedented clarity and groundbreaking insights into the universe. The transition from early observations to the technological wonders of the James Webb Space Telescope highlights the continuous progress in our understanding of the universe. The Hubble Space Telescope, HST, revealed the vastness of space and transformed key ideas in cosmology. For instance, it captured the iconic Pillars of Creation image in the Eagle Nebula, showcasing a stellar nursery formed by massive columns of gas and dust. Another key achievement was the Hubble Deep Field, which captured thousands of galaxies in what appeared to be an empty patch of space. The HST also investigated exoplanet atmospheres, detecting elements like water and organic molecules in distant worlds, suggesting the possibility of habitable zones beyond our solar system. Following the discovery of the nearest observed supernova, SN 1987A, it shed light on the light patterns of massive stars. These achievements solidified the HST's legacy as a cornerstone of modern astronomy, captivating the world with its stunning cosmic discoveries. Its successor, the James Webb Space Telescope, JWST, was launched to build on the technological advancements and lessons learned from Hubble. One example is our understanding of the universe's origins, which is currently explained by the widely accepted Big Bang theory. Approximately 13.8 billion years ago, the universe began as a hot and dense singularity, rapidly expanding to form matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of particles, stars, galaxies, and the various structures observed today. The Big Bang theory also explains the cosmic microwave background radiation, element abundance, and the large-scale structure of the universe. Despite its broad acceptance, the Big Bang theory faced skepticism and challenges in its early years. Alternative models, like the steady-state theory, proposed a universe without a specific beginning. Concerns arose about the evidence supporting the singularity, the expansion process, and observed inconsistencies. Many of these issues were addressed over time, with significant evidence emerging from the discovery of cosmic microwave background radiation in 1965. This discovery, the cosmic microwave background (CMB) radiation, provided the strongest evidence yet for the Big Bang theory. It revealed a faint glow of radiation uniformly distributed across the universe, a remnant of the intense heat from the early universe as it expanded and cooled. The detection of this radiation solidified the Big Bang theory as the leading explanation for the universe's origin. As our understanding of the universe evolved, the scientific community developed tools and technologies to explore the universe in greater detail. Instruments like the Hubble Space Telescope revolutionized our ability to observe distant galaxies, nebulae, and other celestial phenomena. Yet, despite its significant achievements, there were limitations to what Hubble could accomplish, particularly when it came to observing the universe's earliest moments and its faintest objects. The James Webb Space Telescope, JWST, was designed to address these limitations. Unlike Hubble, which primarily observes visible and ultraviolet light, the JWST is optimized for observing infrared light. This optimization enables the JWST to peer through dense cosmic dust and reveal objects hidden from Hubble's view. Its sophisticated design allows scientists to explore the universe's earliest moments, tracing the formation of the first galaxies, stars, and planetary systems. One of JWST's most impressive features is its ability to study exoplanets in detail. By analyzing the starlight that filters through an exoplanet's atmosphere, scientists can identify elements such as water, carbon dioxide, and methane. These findings could provide crucial insights into the potential for life beyond Earth. The telescope's location at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth, offers a stable environment for observing the cosmos. Here, the gravitational forces of the Sun and Earth balance the centrifugal force of the telescope's orbit, allowing it to remain in a fixed position relative to the Earth and Sunday. This stability minimizes interference from Earth's atmosphere and light, providing a clear, uninterrupted view of the universe. Transformative discoveries. Since its launch, the JWST has already made transformative discoveries. It has captured images of ancient galaxies formed just a few hundred million years after the Big Bang, providing invaluable data about the early universe. These observations challenge existing theories about galaxy formation, as they suggest that massive galaxies formed much earlier than previously thought. The JWST has also unveiled the detailed structure of distant nebulae, the cradles of star formation, shedding light on the processes that govern the birth and death of stars. Additionally, it has identified complex organic molecules in interstellar space, deepening our understanding of the building blocks of life. One of the most groundbreaking revelations involves the telescope's ability to observe phenomena that challenge the current cosmological model. For example, The discovery of mature galaxies at the edge of the observable universe raises questions about the speed of their development, prompting scientists to revisit the fundamental principles of cosmology, redefining our place in the universe. The JWST's discoveries are not just scientific milestones. They are philosophical ones as well. By unveiling the secrets of the cosmos, the telescope invites humanity to reconsider its place in the universe. Its findings remind us of the vastness of space, the complexity of cosmic processes, and the intricate interplay of forces that led to the formation of stars, galaxies, and eventually, life on Earth. As we continue to explore the universe with tools like the James Webb Space Telescope, we deepen our understanding of our cosmic origins. Each discovery brings us closer to answering some of the most profound questions. Where did we come from? Are we alone in the universe? What is the ultimate fate of the cosmos? The JWST represents not only a technological marvel, but also a symbol of humanity's unyielding curiosity and desire to understand the unknown. Its contributions will resonate for generations, inspiring future explorers and scientists to push the boundaries of knowledge even further. For infrared perceptions, this ability is significant for contemplating the early universe, since light from the first systems has been extended into the infrared range due to the development of Room, one of the JWST. It was the two notable disclosures, distinguishing proof of systems that existed only a couple 100 million years after the Big Bang. These perceptions challenge well-established hypotheses about system arrangement and advancement. Some of these systems appear more developed and enormous than previously expected, recommending that the cycles overseeing star arrangement and world get-together may have been more rapid and proficient in the early universe than current models foresee. Moreover, the JWST has given unrivaled experiences into the climates of exoplanets by breaking down the light that goes through an exoplanet's climate as it travels its host star. The telescope can recognize the presence of different components and intensifies. This has prompted the discovery of water vapor, methane, and even carbon dioxide in the climates of far-off planets, raising captivating conceivable outcomes about the tenability of these worlds. The JWST's capacity to look into the heart of star-forming locales has also uncovered unpredictable insights regarding the birth of stars and planetary frameworks. For example, it has caught shocking pictures of protostars encompassed by twirling plates of gas and residue, giving a brief look into the cycles that lead to the development of nearby planet groups like our own. These revelations are not just reshaping how we might interpret the universe's beginnings, but also provoking researchers to reconsider a portion of the central standards of cosmology. The discovery of profoundly evolved structures in the early universe has prompted inquiries concerning the nature of dark matter and dark energy, two baffling parts that together make up about 95% of the universe's total mass energy content. As we continue to examine the information from the JWST, it becomes progressively evident that the universe is definitely more perplexing and dynamic than previously imagined. Each new disclosure adds one more part of the riddle, carrying us closer to noting significant inquiries about the nature of existence, the starting points of life, and our position in the universe. The excursion of investigation is far from over. The JWST represents a grand accomplishment in humankind's journey to grasp the universe. Yet it is also a sign of how much there is still to learn. With each picture and data set it conveys, the telescope inspires new theories, new innovations, and a re-established feeling of wonder about the universe. Agreeing with tremendous blast assumptions, space missions like COBE and WMAP, alongside mechanical headways, further maintain the speculation. Exact assessments of inestimable microwave background radiation matched hypothetical checks amazingly well. Enter the James Webb Space Telescope, JWST, outfitted with cutting-edge infrared instruments capable of looking through enormous residue mists. Working basically in the infrared range, the JWST catches the most established light in the universe, noticing objects that formed not long after the Big Bang. Its infrared abilities permit it to focus on star-forming areas, heavenly nurseries, and the introduction of stars, darkened from optical telescopes. Infrared light, with longer frequencies than apparent light, can infiltrate interstellar residue-class mists, beating a restriction of the Hubble Space Telescope. The JWST can identify cooler objects radiating primarily in infrared, making it ideal for contemplating peculiarities like exoplanets, brown dwarfs, and far-off systems. As divine bodies move away, they radiate light that stretches, causing a redshift. The JWST's infrared abilities identify these redshifted signals, catching light from the early universe and offering experiences into its advancement and improvement. Occasions like dark hole arrangements or new star births predominantly transmit in the infrared, further expanding the JWST's observational capacities. The telescope can study peculiarities that would otherwise remain secret, whether visibly or undetectably. The JWST complements optical telescopes like Hubble by offering improved awareness and the capacity to recognize infrared radiation. This ability permits it to peer further into space and dive deeper into infinite history, uncovering stowed-away secrets and providing a more extensive perspective on the universe's development. The JWST serves as our window into the beginning phases of infinite development. Recently, it uncovered something so unprecedented that it could provoke a re-examination of the whole cosmological model of the universe. Space experts found gigantic cosmic systems at the very edge of the perceptible universe. These old cosmic systems existed only a couple 100 million years after the Big Bang, marking the universe's earliest stages. The astounding part is that we're unsure how such enormous structures formed so early in the universe's history. This revelation may lead us to reconsider how we might interpret the development and formation of systems in the early universe. Considering early systems is essential for disentangling the mysteries of the universe's beginnings. The JWST gives insights into how worlds, stars, and planetary frameworks shaped and advanced over billions of years. These perceptions also contribute to broader inquiries concerning the central nature of the universe, including its organization, structure, and the forces governing its development. While the Hubble Space Telescope was instrumental for its time, it had limits in noticing the early universe. Its primary limitation was its inability to penetrate successfully vast residue and identify the infrared light radiated by old systems. Older telescopes relied on visible and ultraviolet light observations, making it challenging to investigate the early universe, where these frequencies are absorbed or distorted by cosmic residue and gas mists. The James Webb Space Telescope represents a significant leap forward in noticing systems from the universe's earliest stages. Unlike its predecessor, the JWST can observe heavenly objects that formed within a few 100 million years after the Big Bang, utilizing its infrared awareness and advanced imaging abilities. The JWST has uncovered a wealth of ancient cosmic systems, offering phenomenal clarity and detail in understanding the universe's early history. Early discoveries from JWST observations have shaken established cosmological models, providing detailed data that challenge several aspects of prevailing hypotheses. This has prompted cosmologists to re-examine core principles governing our understanding of cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates among researchers. JWST observations have revealed more worlds in the early universe than expected by existing models, suggesting a more complicated and rapid development process. Some observed early universes appear surprisingly mature, challenging conventional models that predicted slower development. These surprising findings from the JWST have significant implications for our understanding of the universe's formation and evolution. If early galaxies developed more quickly and robustly than current models predict, it suggests that the processes driving star formation, galaxy assembly, and the accumulation of mass in the universe were far more efficient in its infancy than previously believed. This raises questions about the role of dark matter and dark energy in shaping the early universe, as well as the interplay between these mysterious forces and visible matter. Additionally, the unexpected maturity of these ancient galaxies could mean that certain assumptions in our cosmological theories require revisiting. For example, the timing and efficiency of molecular gas cooling, a key factor in star and galaxy formation, may need to be reevaluated. Alternatively, it could suggest that there are unknown mechanisms at play that accelerated the formation and growth of these structures shortly after the Big Bang. The JWST's ability to peer into these distant epochs also sheds light on the origins of chemical elements and the conditions that gave rise to the first stars and galaxies. By analyzing the light from these ancient objects, scientists can identify the signatures of elements such as hydrogen, helium, and trace amounts of heavier elements, providing a window into the universe's earliest chemical compositions. This, in turn, informs our understanding of how the first stars enriched their surroundings with heavier elements through nuclear fusion and supernova explosions. Beyond the study of early galaxies, the JWST's capabilities are transforming the field of exoplanet research. By examining the atmospheres of exoplanets as they transit their host stars, the telescope can identify the presence of molecules such as water vapor, methane, and carbon dioxide. These discoveries have profound implications for the search for life beyond Earth. The ability to detect biosignatures, chemical markers that could indicate the presence of life, on distant planets represents a major step forward in our quest to answer one of humanity's most profound questions. Are we alone in the universe? The JWST's unprecedented sensitivity also allows it to study planetary systems in their formative stages. Images of protostars surrounded by disks of gas and dust provide invaluable insights into the processes that lead to the formation of planets and moons. By studying these early stages of planetary system development, scientists can gain a deeper understanding of how systems like our own solar system emerged and evolved over billions of years. In addition to these groundbreaking discoveries, the JWST has unveiled stunning views of stellar nurseries, regions where new stars are being born. These images reveal intricate structures within clouds of gas and dust, showing the complex interplay of gravity, radiation, and turbulence that govern star formation. The telescope's ability to capture these details not only enhances our knowledge of the physical processes involved, but also inspires awe and wonder about the beauty of the cosmos. As the JWST continues to collect data, its findings are expected to refine our understanding of the universe's history and structure. Each new observation contributes to a more comprehensive picture of how the cosmos evolved from its earliest moments to the vast, dynamic expanse we observe today. The telescope's discoveries are not only reshaping our scientific knowledge, but also challenging us to think more deeply about the nature of existence and our place within the universe. The journey of exploration is far from over. The JWST represents a monumental achievement in humanity's quest to understand the cosmos, yet it also serves as a reminder of how much there is still to learn. With every image and data set, the telescope opens new doors to discovery, inspiring fresh hypotheses and technological advancements. It rekindles a sense of wonder about the mysteries that lie beyond our reach, driving us to continue exploring the unknown. As we delve deeper into the universe's past, we are brought closer to answering fundamental questions about its origins, its destiny, and our role within it.